Check, check. Okay, I've got 5 minutes. Adair, can you hear me okay?
Yes,
Adair?
I can hear you.
Okay,
Yes.
I'll be right back. We'll get started in just a minute. Everybody home, y'all can hear me okay? Yes. Can see my shared screen? Okay.
Yeah, we can
Right.
hear you.
How's it going, everyone? Have a good weekend? Yeah. All right, so that quiz problem I gave you at the end of class last time was due today. Hopefully you uploaded that to the web. I think, William, you had asked me if I got it. I don't know, I haven't had a chance to check, but I'll let you know if I didn't get it.
Yeah, I was worried because the first one I didn't convert it correctly, and then I tried to send the second one, and I don't know if you got the second one.
Okay, well, I know you were working on it, so don't worry about it. Okay, so we are done with that section on surfaces, solids of revolution. We did all the different variations where you have different axes of rotation. And then we did that weird thing at the end of class where we did these cross sections, perpendicular cuts, those problems. And now we move on to 7.4 and 7.5. We'll cover both of these in one day. It's really an extension of the ideas that we've actually learned, which is the power of the integral, right? To add things up. So the first section here is called arc length. And what I'm going to do is kind of derive, first of all, the idea and then the formula. So one thing we have not done up to this point is taken a curve. Let's say we've got this red curve here. Let's start it and stop it somewhere. Let's say A and B, right? And let's say that this is y is some function of x. So all the things that we've learned so far are we can find the area under this, right? If we were asked to find the area, we can rotate that around the x-axis and find the volume of that solid. We could rotate it around the y-axis using shells, right? This x-axis would be washers, y-axis would be shells. We can put our axis of rotation below it, above it, left, right, doesn't matter, right? So now this new concept, arc length, okay? And this is actually a lot easier to show in class than it is to show for you at home, but I'll try. I think y'all can kind of see my camera a little bit there. So the idea here is that if we were to take this curve, I need to move it down just a little bit more. So I can reach it. Okay, hopefully at home you can see that. So the idea here is that if I were to take this curve and imagine it like this, right? If I were to take this off the page, take the curve off the page and straighten it out and measure how long that is, that's called arc length. So it's really equivalent to the total distance you would travel if you were walking along that curve. That makes sense? And that's something we haven't done before, right? So to do this, we're going to need an integral, but we need to come up with a formula that will represent that length, all right? So here's how we do it. Remember before, well, of course you remember this, we were cutting this into an infinite number of rectangles, right? There was an infinite number of rectangles in here, and that's how we were doing area. So I want us to just imagine this first rectangle here. I'm going to zoom in on this, all right? I'm just going to zoom in on that rectangle that's here. So what we would see here is the curve coming through, right? And then we would have one edge of the rectangle here, right? And the other edge of the rectangle over here. And what we normally did was approximated this like this, and we would have this little error, right? This little region right here that was error. And that would go away as the width of the rectangle went to 0, as the number of rectangles went to infinity. So I don't want us to think about that right now. What I want us to think about is if we were to approximate the length of this red curve between where the rectangle hits here and here, we could approximate it with a straight line, right? So just connect, connect this point to this point with a straight line. And that would be a pretty good approximation of how long this little red piece is. Now there's error, right? But as the width of these rectangles goes to 0, then that error should get smaller and smaller and smaller. Do you all agree? So in the limit, it would basically, they would go and become the same thing. So we need to figure out, can we come up with a formula for the length of this black piece? And it's actually a lot easier to do than you might think. We're just going to do a triangle. Okay, so does everyone see here this triangle that goes across here like this? So if you think about it, we already know how wide this triangle is, right? What has that been for us this whole time? Dx, right? This was our little change in x, right? And then this side of the triangle should be our change in what? Not x, but
Y.
y, right? That should be our little infinitesimal change in y. So let's call that dy. And so that piece here that goes across the, well, that's the hypotenuse, right? The hypotenuse of this, I'll call it h, we don't need to, but we can solve for h using Pythagorean, can't we? We know that a squared plus b squared is c squared on a right triangle. So for us, that would be dx squared plus dy squared should equal h squared. We're not interested in h though, right? We're interested, I mean, sorry, in h squared, we're interested in h. So we'll need to take the square root on both sides, right? So let's take the square root on both sides of this. Dx, you know what? I want to change my notation here a little bit. I'm going to put those dx and the dy in parentheses just to make sure you understand we're squaring that little dx and squaring the dy. I don't want you to think it's like a second derivative or something like that. So I'm squaring h1. So now I take the square root of dx squared plus dy squared equals h, right? So that is the length of one of those little infinitesimal pieces that would approximate the red curve. Remember, we zoomed in, right? So we imagine we have an infinite number of these little guys. So we need to add them up, right? So right now, if we try to use the integral, where do you think our integral is going to start? Well, where is it started when we're doing rectangles for areas? At A and stop at B, right? So far, it looks like our integral should look like this. Integral A to B, and then the thing we're adding up, right? Which is just the square root of all that stuff. So it's just square root of dx squared plus dy squared. And that should be it. But there's a problem. Okay? There's a problem here because in all the integrals we've had, haven't we always had either a dx out here or a dy out here? Haven't we always had that? And that's been an important aspect of all the integrals we've ever done because that keeps track of the variable. It kind of lets you know what the variable in the problem is. So we don't have, do y'all see we don't have a dx or a dy sitting on the outside of that root? Okay, that is a problem. So it's an easy fix, okay? Easy fix. I just now need to remind you of something. Recall that when you have y equals a function of x, right? When we start off with y being a function of x, if we're asked to take the derivative, right, with respect to x, the derivative y prime is equal to f prime of x. But using Leibniz notation, the left side is dy dx equals f prime of x. So all this is dy dx is just a different notation, right? But look at this right here. This is an equation, right? This is an equation. So I can multiply both sides of this by dx, by that little differential, and I get dy. I get an equation for dy. It's f prime of x dx. That's what dy is. So what I'm going to do is where I have dy there in this integral, I'm going to replace it with f prime of x dx. Now I'm out of room, so I need to go to a new page. Are there any questions what I've done so far? Let me move this up here. Let me move this up. Move that up. Okay, so here's where I am. Now I'm going to replace that that dy with dx squared plus, okay, f prime of x dx squared, right? That's where we are. Now, this is f prime of x times dx. So since I have multiplication between those, can't I apply the squared to both of them? Okay, so this will become a to b square root dx squared plus, I'm going to write it this way. It's the f prime of x, but I've got to square that. So I'm squaring the f prime, and then times the d of x squared, like that. It's okay. Now, do you see what they both have? They both have a dx squared, right? So I can factor that out. It's still underneath the root, but it's factored out. And when I factor that dx squared out, I get dx squared. Then in parentheses, I don't like that square root. Okay, I get what? What happens when I factor out x, dx squared there? Plus 1, right? So 1 plus f prime of x, that thing squared, right? Close parentheses. So we pulled the dx squared out of both of those. And now you have multiplication there. So if you have multiplication between two things and you're taking the square root, you take the square root of each one, don't you? And so when I take the square root of dx squared, the square goes away, I just get the dx, right? And then everything else is still there. So watch the way I write this. I'm going to do integral a to b. I'm actually going to do the square root part first. 1 plus the derivative of f squared. And then the dx that was sitting in front, right? I'm going to just push it to the back, dx. There you go. This is the formula. All right. This is it. If you have a function y equals f of x, if you have a function y equals f of x, right, and you want to know the length of this curve between a and b, then you need to be able to calculate this integral. The integral from a to b of the square root of 1 plus the derivative of the function squared dx. Understand? Okay. Just some alternate notations. You might see this written this way: integral a to b square root of 1 plus, you might see y prime squared dx. Same thing, right? If y is a function of x, you might see integral a to b square root of 1 plus dy dx squared dx, because dy dx is y prime and y prime is f prime. So I mean, it's all the same, right? Okay, this is actually the one that you're going to see. I should mention to you that at this point in the class, there are no more notes online for this class. Like in the beginning, I had notes for most sections. We've gotten to a point where I don't like to have notes because I never know exactly how I'm going to go through the material. So everything I'm putting up here, I'm going to create a folder later today, and it'll be a shared folder. And every day after I finish my notes, I'm going to just upload the notes to that folder. So there's a lot of stuff here. Don't try and copy it all down. It'll be available to you later. Okay. All right. Any questions? No? Okay. Let's do an example. All right. I think it's worth doing an example. So what do we want to find the length of? Let's try just something very, very simple, like x squared. All right, let's just try. Let's see if x squared is even doable. All right, so let's find the length of y equals x squared on the interval 1 to 3. So we don't need a picture, right? We don't need a picture, but I'll draw one. Okay, I'll draw a quick graph of y equals x squared, but only from 1 to 3. And the value of 3, or the function at 3 is 9, right? So we got this curve. Oh, gosh. Oh, shit. That's like the worst problem. Okay, whatever. You get it, yes? We're trying to figure out this length right here. How long is that curve? If we took it off the paper and stretched it out, or if you were walking along it, how long is that walk? Got it? All right, so we need the formula, right? The formula is integral from a to b, square root of 1 plus, I'm going to go dy dx squared dx. All right, well, we need the derivative, right? There's some work we need to do here. We need the derivative, we need to square it, we need to add 1, right? Do all that and put it under an integral. So what I like to do is on the side, I like to do scratch work, okay? I start off y is x squared. Okay, what's dy dx? So take the derivative of that, you just get 2x. Okay, I'm going to need to take that dy dx, and I'm going to need to square it, and that's going to be 4x squared, right? So I think I'm ready to go put everything into the integral. Y'all ready? This integral is going to start out at 1 and end at 3. Those are my limits of integration. I'm going to do the square root of 1 plus the derivative, right, squared, which we just found was 4x squared dx. There we go. And how would you integrate that? Trig sub. This would be a trig sub problem because you've got the square root, right? You've got like a squared plus x squared or a squared plus u squared, however you want to look at it, right? And that would not be super easy because you also have to worry about that 4, right? The 4 is an issue. You'd have to factor the 4 out. So I don't know, maybe there's a formula. Maybe there's a formula. Let's see. Let's go to our formula sheets. Is there a formula for this one already? I've got my fingers crossed here. Do we have one? Hey, look at this. Look at formula number 21. If you have the square root of a squared plus u squared, right? Hey, hold on a second. I need to open up another program here. Okay. So we can use this, yes? This formula? It ain't pretty, but we can use it, can't we? Oh. All right, so if I'm going to use this formula, I need to get rid of that 4. So I need to factor a 4 out of both of these. Yeah? So if I factor out a 4, let me do this kind of right over here. If I factor out a 4, I'm going to have a 1/4 plus x squared, right? That's what it'll be if I pull a 4 out of both of those. And then that 4 can come out of the root as a 2. So this new integral becomes 2 integral 1 to 3 square root of 1/4 plus x squared dx. And now I can use the formula because I've got something squared, right? A squared plus u squared, u is x. What's a for us? 1/2. Okay, so I'm going to go to the formula. You ready? All right, this should be equal to, all right, I have a 2. Don't forget 2 out front, okay? And now this antiderivative, remember, u is x and a is 1/2. So this will be x over 2 square root of 1/4 plus x squared plus a is 1/2. So 1/2 squared is 1/4 over 2 natural log of u, which is x, plus the square root of 1/4 plus x squared. Let me move this all down a little bit. Nope. Does anyone have any questions? There's the antiderivative. Evaluate that 1 to 3. And now it would just be a matter of plugging numbers in, right? I'm not going to do it. All right. But you understand at this point, just plug and chug. Now, just so we have an answer, I'm going to go to a website and do it. So I'm going to ask Wolfram Alpha to give me the definite integral from 1 to 3. Let me put a 2 out here in front. And it was the square root, right, of 1 plus 4x squared dx. You don't see that all right? Here we go. Oh, it's going to, what, the 2? What 2? Oh, yeah, sorry. Yes, we had already. Thank you, Christian. Christian pointed out the 2 shouldn't be there because the 2 is when I factored out the 4. We're not. I just went back to the original integral. Thank you. And then also, if I, oh yeah, it did give me an approximate answer. Okay. All right, let me do it again. Come on, man. Do I have to hit this? What happened? Yeah, let me see. I don't know if it'll, let me refresh it and see what happens. It doesn't know what's going on here. I have no idea what's going on. Okay, but we could get the answer. All right, I'm not gonna. It keeps on loading the last question, so I'm not sure why it's doing that. All right, so just take half of this answer, right? There you go, half of that answer. That's how long it is. What do you think? So, you know, really all we have to be able to do here is take the derivative of the function and square it, right? Add 1, put it under a root, and hope we can integrate it. In general, it's a very difficult thing to do without a computer. It's very difficult to just take some arbitrary function and try and do it. Like think about a function that it might be worth us trying. I mean, just think of a function you'd like to know how long it is. I don't know. How about sine? You want to try sine? Look at this. Let's look at the sine curve, just that first arc of sine. Let's just see, how long is that little arc? Is that even going to be doable for us? So if we take y equals sine x and we do it on 0 pi, let's find the arc length. All right. So do I need to draw it? We understand what the one arc of sine looks like, right? All right, so we need a derivative. So I need my derivative over here is cosine x. Oh, I need to square that. Using a slightly different notation here, it's just cosine squared x, right? So that's all I need. Just set the integral up, right? Okay, so the integral is going to go from 0 to pi. And then it's going to be the square root of 1 plus cosine squared x, not minus. Gosh, I wish it was minus, but it's not. It's plus. How do you integrate that? All right, let me close my browser. Let me reopen. Let me see if it will just, let me see if it can even find the antiderivative of it. All right, let's not even do the definite integral. Let's just do square root of 1 plus cosine x squared dx. It found something. The square root of 2 capital E of x with this bar and 1/2. What the hell? Oh, this right here is the elliptic integral of the second kind with a parameter m equals k squared. Okay, that basically means that this is beyond the scope of this class. All right, we cannot, there's nothing that we can do that we can by hand find the antiderivative of that. I think I told you all this early in the semester. If I didn't, I'll say it again. If you were to take a bucket and fill it with all the functions that exist out there, okay, all of them, and you close your eyes and you reach in there and you grab a function, the probability that you can integrate it by hand is 0. Not 0.00001, 0. Essentially, you have no chance. You have to actually go into the bucket and be like looking for something you can integrate. Oh, there we go. So when you look at all the functions in mathematics, for anyone who's like math major, when you look at the bucket of all functions, we start grouping them up. We say, okay, well, we have another smaller group in that group called integrable functions. Those are ones that you can find the antiderivative of. You know, we have differentiable functions. So we try and make it a little easier, but in general, most functions that come up in the real world, we're not going to be able to integrate, which means we have to have a way, because the computer did something, right? In fact, let me go back. Let me put the definite integral in. Okay, so the definite integral went from 0 to pi, right? And it was the square root of 1 plus cosine x squared dx. And I'm going to put in here a 1.0 because that'll help the computer not try and give me an exact answer. See what happens. Hopefully it knows that's pi. Yeah. Look, boy, it had no problem with that. 3.82, right? So I just told you that the computer is telling us we cannot integrate that by hand, right? Yet it was able to get 3.82 as an answer didn't take the computer much time, right? So what's happening here? What's happening is that the computer is using series. It's using power series, which is chapter 8 in this class. And so what I'm trying to do is show you or kind of explain to you why series are so important. Because computer science people, that's how you get around this thing where you can't integrate or you can't differentiate by hand. You basically turn everything into its power series, and then you can get an answer that's as close to the real answer. See, this is a decimal, right? It's an approximation of the answer. It may not be exact. Just like 1/3 is a fraction, right? 1/3, you could say 0.333 and stop. That would be an approximation. The more threes you have, the better the approximation, right? The way this is working is it's giving us an approximation. If we're not happy with that approximation, we can ask the computer to get more precise. And power series allow you to get as close to the true answer as you ever need to be. So even though it may not give you the exact answer, it'll give you an approximation out as far as you want it to go. So if you're building, if your company is making ball bearings for tricycles, you don't have to be that precise with these ball bearings, right? I mean, it's a freaking tricycle. There's a 15-pound kid on it. Who cares, right? But if you're building ball bearings for a jet engine or something, something that has to be, machined down to, the, I don't know, 1,000th of an inch or something, then you need to be more precise. So in the real world, you don't need exact. Does that make sense? Because we can't actually physically make things that way. There's always going to be some plus or minus of uncertainty there, right? So, okay. All right, so understand, it's a pretty simple idea. Derivative squared plus 1 square root. Cross your fingers, hope for the best, right? Okay, let's try one more. And I don't know how this is going to go. I'm not going to make any promises, but do you remember we took some time, we've taken some time in this class when we were learning about areas under curves. We proved that the area of a circle is pi r squared. And then when we learned about these solids of revolution, we were actually able to prove that the volume of a ball is 4/3 pi r cubed, right? Remember, we proved those. We did. So if we're doing arc length now, what is it that we can do? What kind of proof can we do here? Where do you think I'm going with this?
Circumference.
Circumference. Why don't we take the circumference of a circle and prove that it is, what's the circumference of a circle? Diameter times pi, or 2 pi r, right? So let's prove it. Maybe, maybe, all right? So prove the circumference of circle with radius r. Let's do capital. We'll do little r. Is 2 pi r. Okay, so now this is the third time I've done something like this. Third time. The way we did it, we started with the idea of just a general circle of radius r, right? General circle of radius r. And then we said, oh, well, the equation of that circle is x squared plus y squared is r squared. And then we solved it for y, and we got y is the square root of r squared minus x squared. And this is the thing that was our function, right? We found the area under it, and then we also revolved it around the x-axis. If you look back in your notes or in your memory, when we did the area, the integral became a trig sub. But when we did the volume, because of the volume formula, there was a squared in there. It actually was a straightforward integral, just power rule. It was really kind of simple. What are your thoughts? What do you think? Just your initial kind of feeling. Do you think this is going to be easy or hard? You think easy? What do we have to do in this? For an arc length, we have to do the derivative of that squared plus 1 under a root, right? Okay, I don't know. Let's see. Okay, so where are we going to integrate from? Okay, so what arc length are we going to do? We can't do the whole thing because it's a circle. It fails the vertical line test. So where do you want to integrate from?
First
Quadrant
quadrant.
1, 0 to r, yeah. Let's go 0 to r. So really, everyone, all we're going to do is try and find the arc length of this piece. Okay, that's it. If we can find the arc length of that, we'll just multiply by 4 because of the symmetry. In fact, I think I'll put it into the formula right now. I'm going to put 4 times the integral from 0 to r, and then square root of 1 plus. Now I have some work to do, right? I have some work to do. I need to go take that function. This is my function. I need to take it over here. I need to find its derivative. All right, taking the derivative of that. Remember, r is a constant, x is the variable. So that's chain rule, right? Cal 1, derivative of the square root of something is 1 over 2 times the square root, right, of that something, times the derivative of what's under the root. What's the derivative of what's under the root? Just negative 2x, right? R squared is a constant. The 2's cancel. Oh, I forgot to put the prime here, sorry. So that means y prime is just negative x over the square root of r squared minus x squared. And what are we going to need to do with that? Square it. So let's square. Oh, that's nice. I'm happy to see the squared, aren't you? And you take that and square it. So I square the top, I just get x squared, the negative goes away, and I square the bottom, and hey, the square root goes away. I'm actually kind of excited about this now. Right? Square the top and bottom, this ain't bad. I still need to add 1 to it though, right? So I think it's ready to go into the integral. Let's put it in here. Any questions? dx, dx, dx. All right. That doesn't look very good, does it? That doesn't look very good. Any ideas on what we could do? I mean, just maybe some algebra first. How about the 1 plus the fraction? Can we put those together, maybe with a common denominator? Maybe it'll go somewhere. I don't know. Let's try it. How would you put that together with a common denominator? You'd have to turn the 1 into a 1 over 1, and then turn the 1 over 1 into what? R squared minus x squared over r squared minus x squared, right? Okay. So this is 4 integral 0 to r square root. I'll write it out. R squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared dx. All right, you can put those together now. Ooh, what happens up top? What do you get? Just r squared, don't you? So 4 integral 0 to r, you get just r squared on top, right? Everyone good with that? R squared minus x squared plus x squared, the x squareds cancel, you get r squared on top. So r squared over your common denominator, all underneath the root. And because you have a fraction and a square root, right, of a fraction, you can do top and bottom separately. So the square root of the top is just r, isn't it? And r is a constant and can come out of the integral completely, right? Completely out of the integral. So I have 4r integral 0 to r, 1 on top now, square root of r squared minus x squared dx. Questions with that? Now, can you integrate this? Yeah, trig sub, right? Do we have a formula? I think we have a formula. Well, I know we do, but we go take a look at our formulas. Do we have something where it's 1 over the square root of a constant squared minus the variable squared? Formula is 16, right there. Right, that's our formula. So using that formula, A for us is what? A is r, right? So we're ready. We're ready for the antiderivative here. It's 4r, that's on the front, times, it's just arc sine of u over a. For us, u is x, and a is r, right? And we're evaluating this from 0 to r. Who's got questions? It's actually looking pretty good, huh? We got the antiderivative. I mean, that's the hardest part of these problems is there an antiderivative? All right, so evaluate, plug r in first. Okay, so if we plug in r, we get 4r times arc sine of, well, r over r is 1, isn't it? So arc sine of 1 minus, now plug in 0, 4r arc sine of 0, because 0 over r is 0. And I hope now we're Cal 2 students, right? Wanting to be engineers and computer scientists. I hope we all understand what arc sine of 0 means. All right, at what angle is sine 0? And this one is at what angle is sine 1? So what are these? What is this? I put too much, 5 or 2? And then minus over here, what's arc sine of 0? 0. Gone, and your answer is, well, the 4 and the 2 reduce out, right? 2 pi r. There you go. So that wraps it all up, okay? We have shown in this class that if you have a circle of radius r, that the circumference is 2 pi r. We've shown that the area is pi r squared. And we've also shown that if you take a ball of radius r, that the volume is 4/3 pi r cubed. We've done it all with calculus, right? All right. So everything we've done up to this point, our curve has been a function of x. What if our curve is a function of y instead? Understand? Like these have all been functions of x. So what if we have a function of y? I have good news. Not much changes. If x is some function of y, g of y, I'm going to call it g of y, on some interval CD, right? On some interval CD, then here's what we're looking at. Some curve does this, C to D, and we want to know how long that curve is. Well, it's the exact same thing, okay? Because our rectangles this time would go this way, right? And if we zoomed in on that piece, we'd still have a triangle, okay? We'd still have, well, let me use a different color. Let's say if this rectangle came in here like this, okay, if you zoomed in on that, you'd have your rectangle, you would have your curve coming through like, oops, coming through like this. And you could still create a triangle like this. We could still call that H, and this is still dx, and this is still dy. Which means you have the exact same formula because you're still going to do dx squared plus dy squared. Understand? So everything stays the same. Now the formula does look different, but let me show you the setup. I'm not going to go through the whole setup again. But here's what it'll become. It'll become the length of this will be the integral from c to d, but square root of, what do you think? 1 plus
X prime of y?
the derivative of x, right? Or g prime, or there's different ways to say it. There's 3 different ways to say it. We could say x prime squared dy, not dx. Or you could do integral c to d of 1 plus g prime of y squared dy. Or you could do integral c to d square root of 1 plus dx dy, not dy dx, dx dy squared dy. All 3 of those will give you the same result. Okay? So you're still going to have to take the derivative. You're still going to have to square it. You're still going to have to add 1, take the square root, and hope for the best. So I believe I've summarized both of these here in my notes. Let me see here. Here it is. So if I'm going to put this in yellow, that way when you look back at the notes, you'll know what the important part here is. There are 2 formulas for arc length. And here they are. If y is a function of x from a to b, then we're going to take that curve, we're going to straighten it out and measure its length. That length is going to be the integral from a to b of the square root of 1 plus dy dx squared dx. Or this is another, I only wrote 2 of the ways here. Now, if x is some function of y on some interval CD, then the arc length is take that curve, stretch it out, measure its length is this. Oops, this goes down more here. Okay, those are your 2 formulas. I do not believe those are on your formula sheets. Okay. But on your next test, I will allow you to have something where you can put additional formulas on there, because your next test is going to have all the things wrapped around and all that stuff, right? So I will allow you to probably create a little reference sheet for yourself where you have whatever formulas you feel like you're going to need. It'll be only formulas, but I'll allow you to put something together. Okay? You're welcome. I didn't have that when I was a Cal 2 student. We had to memorize all this. It was brutal. I've given you my philosophy on that, right? Told you, maybe not. Like you go take another Cal 2 instructor, they may not allow you to have any formulas at all, not even the ones from the back of the book. I know there are some people who teach it that way here on campus, and I know other colleges same way. And that's just rough. You know, I personally am not someone who can memorize things easily. So, and my philosophy is that in the real world, you're never going to be locked in a room given 3 hours with no resources, right? Even if you're working on a project, even if it's hard, you're usually going to be able to talk to your colleagues. You're gonna be able to reference things, you know? So it's more about, can you access the information? Are you efficient at getting to the information? Not Symbolab, okay? Not just, oh, let me go to Symbolab and get the answer. I'm talking about, like, you know what I mean? Like going to the source of information, trying to figure things out. So I have that philosophy, which is why I will allow you to do something like that for this exam and for the final. For the final, you'll need a lot of stuff. Okay. You might start thinking about doing that now, like start putting together a sheet, 8.5 by 11, front and back, with just formulas and steps, procedures, how to do things. Nothing worked out, no examples worked out. You might start putting that thing together now. That way you're not trying to put it all together like right before the test. And you might have, several versions of it. I don't care if you copy, paste, print, I don't care how you do it. It can be done, typed up. I don't care, just have something, all right? We have 4 more to do today. So the next 4, I think. You know that sheet that I gave you, the handout? Who wasn't here last time? I have a few left in color. This solids of revolution one. This, this is a lot of material, so I don't know how you fit all this, but this is something I would definitely have. Anyone else? This is something I would have. I sent this out electronically already, but I would maybe find a way to try and condense this, the things that you think you need. Okay, we're moving on. Ready? I should warn you that when you do the homework problems for this, the algebra in these get kind of tricky. The algebra gets tricky. In the problem that we did here, this one right here, where we got a common denominator, and when we did that, the numerator became something nice. That is kind of a theme in the problems for homework. The author of this book had to make just in general, you have to pick your problems very carefully if you want the students to be able to figure them out, because the homework problems should all be able to be integrated by hand, right? So when you start doing it, that algebra underneath that root, you're gonna have to mess with things. Common denominator, you're gonna have to see like perfect square trinomials and factor. So just be on the lookout for those sorts of things in the homework. How much the use of computers? Yeah. Oh, math in general? I think computers have allowed us to solve so many things numerically, right? The programs that you cannot do by hand. You just can't, right? So it's been huge advancements, but at the same time, it hasn't solved everything. Like there's a famous math problem called the oh my gosh, I cannot believe I'm having a blank right now. It's one of the $1 million questions. I know exactly what it is. I just can't remember the name of it.
The Riemann hypothesis.
Yeah, the Riemann hypothesis. Yeah, it's basically trying to find the zeros of a complex valued function. It's like finding the x-intercepts of a function, but for a complex valued function. And there's a hypothesis that all of the solutions lie on a vertical line. And we've had a computer checking points on that vertical line for several decades now. We've checked millions and millions and millions and millions of points on that line, and every single one of them works, but it's not a proof, right? 42? Okay, that's outside of mine. I'm sorry.
Supercomputer and Hitchhiker's Guide to the Galaxy, and it spent thousands of years computing the meaning of life, and it gave up 42.
Oh, so that's the number 42. That's right. Okay. Is 42? I thought it was 24. No? Is it 42? I think it is 42. Okay. Now I know exactly what you're talking about. Yeah, so computers have really pushed what we can do, but there are also limitations. So y'all know prime numbers, right? Prime numbers are numbers that are only divisible by themselves in 1. So the primes, we all know the primes, right? Like 2 is a prime, 3 is a prime, 5 is a prime. Is one a prime? 1 is not considered a prime. It's weird, but it's not considered a prime. All right, 2, 3, 5, right, 7, keep going, right? So first of all, are there an infinite number of primes? That's been proven. There are an infinite number of primes, all right? You prove it by contradiction. You assume there's not, and you contradict yourself. Yeah, we're not going to get into proofs, but that's a common way to prove things in math, is that you assume something's true, and then you wind up contradicting yourself, which means it had to have been false. It's like me saying, everyone in here is wearing a hat. Okay, that's my assumption. Everyone here is wearing a hat, and so then I go, oh wait, Christian's not wearing a hat. There, I just contradicted myself. Does that make sense? Okay. So there are an infinite number of primes, right? Now, what's the biggest one we have found, right? So what we actually are doing to figure this out is using computers. It's hard to just find them because you have to check them, all right? You have to check to see if they're prime or not, which is hard to check. So what we do is all these computers all over the country, right? Think of all these universities and stuff that have these computer labs, right? They became part of this program where at night, when no one's in the lab, it runs this program in the background. And so you've got all these computers checking all over the country. And then like a few years ago, maybe 2 years ago, some computer in some obscure place in the country hit on the most recent prime. And it now has that computer at that college has the accolades of, hey, we found the largest prime so far, and who knows when the next one will come. I don't know why we're talking about primes. Computers and advancing, right? I'll give you one more thing. Because I think this is worth it, especially computer science majors. So we send a lot of data, right, back and forth. Phones, right? Everything. We have so much personal data out there. How much of it is private? How much of it is safe, right? So when you log into your bank account, right, you're hoping that stuff is sent. Do you think that if you send something that's encrypted, do you think that is it possible someone could intercept that and decrypt it, you think, or break the code? Yeah, you think so? Do you think that somewhere in some cavern in some building at NSA, they have a way of taking whatever it is and figuring out what it was supposed to say? Only NSA? I'm going to tell you right now, no freaking way they can do it. Okay? No way. All right? That's the danger. Not the danger, it's great, but it's also the danger is that the encryption that we use today, modern encryption, is impossible to break. And here's the way impossible. Let me just show you what it is first, okay? I'm going to break it down, make it very simple to understand. It's a little more complicated than what I'm going to do here, but here's the idea. If I want to send you a message, right? If I want to send, let's say I want to send you a message, but I want it to be something that no one else can hear. What I'm going to do is I'm going to write the message down. I'm going to scramble the letters up, right? Send it to you. It's going to be scrambled. You have to unscramble it now, right? But you have to know how I scrambled it in order to unscramble it. So how do you know? You don't, right? So here's the way it's done. And I've got to go, this goes back to prime numbers. So let's take the number 15. Does everybody here know the prime factorization of 15? 3 and 5, right? Those are the two numbers that multiply to be 15, and they're both prime. So we take two prime numbers, 3 and 5, we multiply them together, we get 15. This is called a composite number. And this is called, well, these are primes, right? Composite, these are primes. All right. So if I yell out to everyone, 15, right? Let's say to break that code, all you have to do is be able to say, oh, 3 and 5 are where the 15 came from. All right. So I'm going to start throwing out some numbers. 21, you could break that, right? Well, here's the thing. There's an infinite number of primes, right? So I'm going to go pick a prime now. I'm not going to tell you what it is. But I'm going to tell you this about that. There's two primes I'm going to multiply together. These two primes that I'm going to pick are 40 digits long. 40 digits. There's an infinite number of primes, okay? So I'm allowed, they're out there, okay? I'm going to pick a 40-digit prime and another 40-digit prime. I'm multiplying them together, and when I multiply them together, I'm getting an 80-digit number. Okay? So imagine that I have this 80-digit number, right? I want to send Cruz, a message, okay? I want to send Cruz a message. Cruz, no, let's do it the other way. Cruz wants to send me a message, all right? So Cruz wants to say something to me. I'm gonna yell out to Cruz my 80-digit number. Cruz, here's my 80-digit number. Everyone can hear it, all right? Everyone can hear that number. Cruz is gonna take his message. He's gonna scramble it using my 80-digit number. Now that process I'm not getting into, but just imagine that he has a way of taking his message that he wants to send to me using my 80-digit number, scrambling it. Got it? It's scrambled. Now he sends it to me. Everyone sees it. His 80-digit scrambled message now comes to me, and it just looks like gibberish, right? The only way to unscramble it is if you knew the two 40-digit primes. Okay, you have to know the two 40-digit primes, which may sound easy, but if I give you an 80-digit number and I ask you to break it down to two 40-digit primes, it would take all the computers on the planet working on that problem, okay, continuously for 10 times the age of the universe. That's the standard we use, all right? So what if computers get faster? I go to 60-digit numbers. What if they get faster? I go to 100-digit numbers. I'm never going to run out of primes. Okay? So it's not about that it can't be broken. Could you get lucky and descramble? Yes, you could get lucky. But if you're just trying to do brute force, is it these two? Is it these two? Is it these? If you're just checking, trying to figure it, having computers do that, as fast as computers are, like I said, all the computers on the planet working on the same problem at the same time, 10 times the age of the universe. So it's essentially impossible to decrypt. That's called RSA encryption. RSA, it's the three letters of the last names of the guys who came up with it. There was a time where if you had that program on a disk and tried to leave the country, you could be arrested for transportation of a munition. That's what they called it, because it was so powerful, right? Does that make sense to you? So if somebody in here someday goes out and figures out a way to break RSA encryption, to be able to to factorize an 80-digit number easily, everything would come crumbling down, right? Everything would come crumbling down. So you'd either like disappear or you become very wealthy. I'm not sure, but society would have a problem because we would have no way to encrypt. I mean, recently, within the last 5 to 10 years, we've had all sorts of crazy violence within our society, right? And there's been terrorism, and they've recovered the phones of these terrorists, and they're using just an app to communicate with each other. It's just a simple app, and the FBI and CIA and NSA, they can't break the encryption. They can't because we all know we can't. It's not a secret. It's not a secret. All right. Proton mail, yeah. 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 The only way it could be broken is if you somehow were on the side of the person. Y'all have heard of a public key, right? Have y'all ever heard that before? A public key? No, computer science. That's the 80-digit number. That's the public thing being broadcast. That's your key. Everybody sees the key. It's like you got your key. I want to send you a message. I take your key. I scramble my message. Here's the message, right? Everyone's got their public key. So when you say a company is like, what do you call it, proton mail? Yeah. So unless you're on the inside of proton mail, right? If you can get on that backside where you somehow see the primes that they're using, then if you're on the outside, you're set. You can't get in, basically. Can't break it. So anyway, All right, well, yeah, there's a very good book called The Code Book. It's called The Code Book, and it is, I read it a couple of years ago. It's kind of a little outdated. The last topic in that has to do with what is it? Just how computers can get faster, but they go from smoke signals all the way to like modern day encryption in this book, and it's a great read if you're one of those people who like to read and are interested in things like that. Yeah. Okay, let's get back to Cal 2. That was fun though. I enjoyed that. We can carry on this conversation another time. All right. So arc length, got it. 2 formulas. Now we start talking about something else.
I don't remember what I asked.
You asked, have computers advanced math?
Yeah.
And they have. I mean, you still have to have a computer find the 2 40-digit primes, which we usually have a list. Okay. I mean, it's easy to generate a prime, but it's hard to break a composite down into 2. Another, one of the most brilliant living mathematicians right now, one of his biggest things right now is trying to figure out, like, if you look at the prime numbers, how much space is between the primes. So like when you look at the numbers, like 2 is prime, 3 is prime, right? There's no space. And then you have, what are the next ones? 5 and 7, there's this gap between those, right? And then there's what? 13, right? And there's 13, then there's 15. I mean, sorry, not 15, there's 13, then there's what, 17, and then 19. So do y'all agree you can never have 2 primes right next to each other? Because all even numbers are not primes. So there has to be at least a gap of 1. So those are called twin primes when they're right next to each other with a gap, 1 space. So he's studying how much space is between primes as you go on. Is there a lot of space? And it seems to be very weird the way it works. It's almost like pi. There's no like rhythm to it. It's just so weird. Okay, we got to move on. All right, so we know the arc length. We've got a formula. Now we're gonna do something similar to what we've done before, but slightly geometrical interpretation. I'm going to take a function of x here, okay? Take a function of x, and I'm going to look at it in 3-dimensional space, and I'm going to wrap it around the x-axis. All right? We've done that before, right? But we've tried to find the volume of that solid, right? Now what I'd like to know is what is the area of that if it's just the outside surface. So not the volume of everything in between, just the area of the outside surface. That's called surface area, right? So we'd like to know what that is. We'd also like to know what would happen. Make this a little bit bigger. We'd also like to know what happened if you take that function of x and you wrap it around the y-axis. That would also give you a surface. And it would be nice if we could figure out the surface area of that, right? And then if we had a function of y, right, instead of x, we'd like to be able to do the same things, right? Wrap it around the y-axis, figure out the surface area of this, or take that and wrap it around the x-axis and find the surface area of this. So all 4 of these things would have different areas, right? So we're going to have some slightly different formulas for each one. Let's just go after this first one, all right? And let's see if we can come up with the formula for it, all right? We're going to try and generate the formula first, which will involve an integral. So we need the little thing to add up. So this is surface area. Surface area of revolution. Basically, we're going to figure out a surface area when we revolve a function around. So let's go back and go to our standard picture that we've been starting these things with. Let's start at A. Let's end at B. Let's take our curve and let's wrap this around the x-axis. All right, we're going to go around the x-axis here. the x-axis. All right, when we do that, do y'all kind of see what it looks like? I mean, I know it's not super easy to draw this, but kind of get an idea of what it looks like. That's what it would look like wrapped around. We want to know the area of this. So the way we're going to do it is this. We're going to take that same idea of a rectangle, but we just want to wrap just that one piece. I apologize, I forgot to mute my phone. Okay, so I want to wrap just this piece around the x-axis. So imagine that going around the x-axis. What do you see? Could you describe to me, like, physically what you see when that's wrapped around? It's like, what does it look like to you? Yeah. How about a rubber band? Kind of like a rubber band would look. It's like really thin, and it would be something like this. Don't see that? That thing wrapped around the x-axis would kind of look like a rubber band. I would like to know the area of that one little rubber band and then add them all up, right? So how am I going to find the area of this? Well, I'm going to do something we've done before. I'm going to cut it. I'm going to cut this rubber band like that. I'm going to just lay it open. If I lay that thing open, it's going to look like this now, right? How wide is this rubber band? Well, we need two things. We need to know what this is, and we need to know what this is. Yeah, so I know you want to say dx. I know that's like your intuition here is that, oh, the width of the rubber band is just dx. It's been dx this whole time, right? But it's this little piece right here. It's how long that piece is, isn't it? It's how long that piece is. Do we know how long that piece is? Isn't that the arc length? It is. I mean, the length of that is the arc length. So this piece right here, and this is the part I think that confuses most students, is this piece right here is actually the square root of 1 plus f prime of x dx. That's how wide that is. This is the arc length. The arc length is the actual width of that rubber band. Now, how long is it, or how tall is it? That's the circumference, right? The circumference, which means you would need to know the radius. You would need to know the distance from here to that top edge. Do we know what this distance right here? That's the function, right? That's this distance here to here. That's f of x. Oops. Here to here is f of x. So this is f of x. So that's the radius of this circle. Y'all get what we're doing, right? We've done this before. I just want to make sure y'all understand. We have this rubber band, right? We've got this rubber band, right? And we cut it open like this. And so we're trying to find this length, right? Which is also the circumference of this circle. But we know that the radius, since we rotate around the x-axis, the radius has to be this right here, which is the function's value itself. And circumference by definition is 2 pi r, right? 2 pi times the radius. So this side over here should be 2 pi times the radius f of x. Am I missing the square? I'm missing the square. Oh, thank you. Thank you. I'm missing the square right there. Appreciate that. Right there. I forgot to put it. So the area of this rubber band, right? The area in here then is just this times this. and then we want to add them all up. Right? So the surface area, which I'm just going to put A, should be the integral from A to B of, I'll start with the 2 pi f of x times the square root of 1 plus f prime of x squared dx. Which is basically the same formula you just got, right? Isn't this the same thing that we did with when we were trying to find the arc length? It's the same thing, but we've added one thing to it, 2 pi f of x. Otherwise, it's the same thing, isn't it? If we compute this integral, we will get the area of the surface generated if you rotate that region about the x-axis. Rotate that region, sorry, if you rotate that curve around the x-axis. So that's your first formula. We will also have a formula if we rotate around the y-axis. We'll have a formula if it's g of y instead of f of x around both axes. So let's start with this one, then I'll give you the other ones. Let's do an example. So the first example, let's take y equals x squared. Let's look at it on the interval 1, 3, and let's rotate about the x-axis and find the area. Understand? We've done a lot of this work already, haven't we? We have, yeah. Because when we do this integral, we're going to have integral 1 to 3, right? And then 2 pi. Now, I'm going to put the 2 pi on the outside. 2 pi will always be in this formula, right? So I can always bring it to the outside. I need f of x, right? What's f of x? X squared. Okay, so x squared integral square root of 1 plus the derivative of this squared. We did this problem earlier, right? It was 2x, and then we squared it, we got 4x squared. Dx. Go back in your notes when I did this one right here, right? This one, right? When we did this, y equals x squared from 1 to 3, we were trying to find just the length of that arc. We did this. We said, oh, crap, we're going to have to go and do this, right? And we found a formula and we were happy. Here, this integral is worse, isn't it? This would take trig sub for sure. We would have to, because we don't have a formula. Well, I don't think we have a formula for this, do we? I don't think we do. Oh my gosh, we do. We do, formula 22. I left my book in the office. There's like books, old books. If you go back and go to a library and, you know, go to a university library and look up like book of integrals, and there'll be books, thick books full of integral formulas. Back before computers, we would have to come up with a formula and then put it down. And that way someone's already done the hard work for you. And that's what engineers would use. You would get to a problem. He's like, oh, we need to integrate this. Let me find that somewhere here. And then, oh, there it is. So you don't actually have to do the integral. Yeah. 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 Because in our textbook, this formula sheet right here, reference page 6, goes up to formula 29. I only let you have these 29, but I think in the back of the book, there's close to 150 formulas. But the first 29 are the only ones I let you use. So here we go. Yeah, I don't feel like doing that. Yeah, I don't feel like doing that. But we have it, at least we have it, right? I mean, that's a good thing, right? That's a good thing. So I guess I'm not going to finish this problem out. On a test, if I want you to find the actual area and take it all the way, I will tell you. I might tell you just set up the integral. And then this is all you'd have to do. Okay. The problems in the homework can be done. They're not going to be super crazy hard like this. They'll be easier to do, all right, because they specially make those problems for you. Yeah, this is much more difficult than integral. So I'm going to say here dot dot dot, and that's just to illustrate how when you change what you're trying to do, go from arc length to surface area, the integral can become not fun. Where do you think I'm about to go? Where do you think I'm headed right now? Y'all ready to go around the y-axis? All right, we can do a y-axis one. I wanted to do one more example. Sine would be the one that we've been doing, right? Do you think that would be? Let's go back and look at the integral. We won't do it, but let's look at the integral for the sine one. This was it, right? And we said, oh, the computer can't do that, right? Could we do the surface area though? What would be the difference between this and the surface area formula? What would be out front? 2 pi. And then there would be a sine out front, a sine x, right? And then the integral of 1 plus cosine squared x. Could you do that integral?
Yeah.
Yes. How?
U sub.
Basic u sub. Let u be cosine x. If u is cosine x, here's its derivative. You're just off by a constant. That's doable. That's doable. So isn't that crazy? You take the sine function, finding the length of the arc is impossible to do by hand. Need a computer. But if you want to rotate it around the x-axis and find the surface area, we can do that. It seems like you shouldn't be able to find the surface area, but the arc length, the length should be easy. It just doesn't work that way. For this problem, it doesn't work that way. Okay, that wasn't the example I had in mind. I'm glad we talked about it, but this would be the surface area. Which one? What do you think I want to do right now? Surface area of a sphere, right? Sphere, right? We've done the area of a circle. We've done the circumference of a circle. We've rotated it around and got the volume of the sphere. What about the surface area? What's the formula for the surface area? That's not as common. People don't. If we go to our formula sheets, it's there. It's a very weird formula because it's so simple. For a sphere, the volume is 4/3 pi r cubed. We have proven that. The area is 4 pi r squared. 4 pi r squared, that's it. By the way, while we're here, I have proven this and this and this. All three of those formulas have been proven to you, right? Or we have proven. I'm not going to say it's all me. We have proven that. Let's prove this last one. We will then complete. I will feel complete that we have done these things, right? Let's try it. I hope we can do it. I mean, there's no guarantee, right? No guarantee. So we want to find, or no, verify, show that the surface area of a sphere of radius r is 4 pi r squared. So somebody tell me again, what are we going to do here? We're going to, what are we doing? How are we going to do this? What are we rotating? What, huh? What are we doing? Yeah, we're going to take that little first quadrant of the circle again, right? Wrap that sucker around the x-axis and double the answer. Right? So we're going to take just this first quadrant of the circle. We already said earlier today that that's the square root of r squared minus x squared, right? Yeah. And we're going to go from 0 to r. And the only adjustment in the formula is this, 2 pi integral 0 to r. But what goes there before the square root? The function itself, right? Which is the square root of r squared minus x squared, right? That's f of x. But then I have to multiply that times the square root of 1 plus something dx. Go back in your notes. Remember we did this part already? Didn't we do this part already? Let's do it. Let's go back in our notes. There it is. Okay. So we had taken that same piece. We had taken this derivative. We had squared it. We had put it right here. Here's where it was, right? Squared. So I'm going to put that where we are. This is x squared over r squared minus x squared, right? But what did we did a common denominator and we did all this, and then didn't we get all of that to just turn into this? This is very simple. Yeah, you see it already, huh? So that all turns into this. So this becomes 2 pi integral 0 to r square root of r squared minus x squared times 1 over the square root of r squared minus x squared. Am I missing? Yeah, we pulled an r out too. Thank you. That r. Yeah, go back when we did all this, right? And we did the square root of r squared on top. We wound up pulling that r out. And that is super nice, right? Because these just go away. And so all you get is 2 pi r integral 0 to r of 1 dx. The antiderivative of 1 is x. So this is 2 pi rx evaluated from 0 to r. And when you plug r in there, you get 2 pi r squared. And when you plug 0 in there, you get 0. And so your answer is 2 pi r squared. Now, what I didn't do, I should have doubled it in the beginning. But remember, this is just the answer for half of it, right? It's the area of half of it. So double that, you get 4 pi r squared. That was easier than the other one, wasn't it? Didn't need a formula. It's kind of weird how that works. And if you go back now and look at it, it was harder to find the area of a circle than it was to find the volume of a sphere. And it was hard, it's harder to find, sorry, did I say that right? No. When we did the area, it was harder than the volume, I believe. Yeah, the area was harder than the volume. And here, the surface area is easier than the circumference, the arc length around it. So just that's the way it works out, you know? It's weird how math works sometimes. All right, good. That was fun. I'm gonna go back over here. I'm gonna highlight that one just because I want to. Yay, we're done. So if you take anything away from this class, at least you've seen where those formulas, those 4 formulas come from. All right, let's look at now the formulas for the other 3 cases. Like I said, I will give you these notes. I will provide them to you. All right. So if y is some function of x on some interval a, b, if we rotate that around the x-axis, your new integral is 2 pi integral from a to b of f of x, and then the square root part, that right there is that little arc length. There's a picture. If it's a function of y, okay, so this is the one we haven't done. If it is a function of y on some interval CD, and we rotate about the x-axis still, okay, still the x-axis, then here's the way the formula changes. You get 2 pi y, and then square root of 1 plus g prime of y dy. We need to do an example of this one because there's something a little bit tricky in this formula. I'm going to copy it. All right, here we go. All right. So here's the example we'll do. Example. Let's let x equal. Now I'm going to make this problem up. So we are not going to be able to do the whole integral. We'll at least be able to set it up though. Okay. So x equals, let's go with y cubed minus y squared. Now let's do this on the interval 0 to 1. Let's make it plus in between them. And we want to take this and we want to find the area of surface if rotated about the x-axis. Very important that I'm telling you what axis to go around. All right, so this is a function of y, right? X is some function of y. Our interval CD is given. We're rotating around the x-axis, so we just want this formula, right? Here's the part that confuses students right here. I'm just going to do 2 pi integral 0 to 1. But look what's in the formula here. Y, right? In the previous formula, we put f of x there, didn't we? We actually put the function, the function of x went there. Here, because this is a function of y and we're going around the x-axis, we are just simply going to put the letter y there, the variable y. And then we will have the square root of 1 plus, now g prime of y. That means you have to take derivative of this, right? This right here, take derivative of this with respect to y, which is what? 3y squared plus 2y, and then you have to square that, and that's all with respect to y. So the part I think that tricks students is this right here. This y, you don't do anything. It's just the letter y. It's just the variable y. That's all it is. Okay? Now I'm going to stop there. That's it. Again, when you do it here, when this is a function of x, you actually have to put f of x here. You don't put x, you put the function f of x here. But when you're doing a function of y around the x-axis, y will just go here. Now the other formulas, see, these are for rotating around the x-axis. There's 2 formulas. If we go around the y-axis, then if you have a function of x about the y-axis, look at the formula. It's just like the one we did just a second ago with the y. You leave x alone and then you put the derivative. Oh, I forgot to put the squared in there. Did I forget to get the squares on the other ones? I just did this. Oh, I forgot the squared here too. My goodness. Check the other ones. Oh my gosh. What the hell? No one noticed that? Forgot to square these derivatives. So these are the other 2. I'm not going to go through examples of these. These are less common, but you have formulas for them here now. Now they're correct. So we'll see how that goes with your homework. You know how when we did volumes, when we rotated and got volumes, it was x-axis, y-axis, but then we did lines, like weird lines all over the place. We're not doing that for surface areas. For surface areas, it's always just going to be x-axis, y-axis. That's it. All right. You could do the others, but we're not going to. All right. 10 minutes. I have one more thing that I'd like to show you. I'd like for us to take a look at f of x equals 1 over x on the interval 0. I'm sorry, not 0. Can't plug 0 in there. 1 to infinity. I'd like for you to find the volume if you rotate the x-axis and then find the surface area. If you rotate around the x-axis. Two problems, A and B. Are you ready? You want to look at it first? We'll look at the picture of this. You all know what 1 over x looks like, right? I want to look at my interval, 1 to infinity. This is an improper integral. One of our limits of integration is infinite. So what this looks like visually is this. We've got this function 1 over x, and it goes out forever, right? Gets smaller and smaller. What we want to do is we want to take this, we want to rotate it around the x-axis. And we get this, right? I'd like to know what, first of all, the volume of that. If it were a solid, right? If that were solid, I want to know what the volume of it would be. And then the second question is, if you're just trying to figure out the area of it, like if you needed to paint the outside of it, how much paint would you need? That would be surface area. The volume would be if you could fill it with something, how much would you need to fill it? But see, it's infinite. So what do you think? Are we going to have infinite volume and infinite surface area? I don't know. We got to figure it out, right? So let's do volume first. If I do volume, how am I going to do it? What method am I going to use? Trying to find the volume. I'm going from 1 here. Here's 1, and I'm going to take this. It goes forever. Oh, what the hell? Goes forever. I want the volume underneath this thing, or the volume if you rotate it around the x-axis. This is last class, right? Or the one before that even. Draw a rectangle, rotate around the x-axis, right? What method am I going to use?
Washers.
Washers, right? You have a top function, bottom function, or an outer radius, inner radius. Yeah. So you have your rectangle over here. You've got your top function here. Your bottom function is just the ground, right? Your axis of rotation is also the ground. So this is where you have to figure out R out and R in, right? RO and R in. And then you just use the formula, right? For washers, which is what? What's the formula for washers?
Pi integral.
Pi integral,
fx
good.
squared.
And we're going to go from 1 to infinity, right?
Yeah.
And then it'll be the outer radius, which for us is 1 over x squared minus the inner radius, which is 0 squared dx. Does everyone understand where this is coming from? Does this integral look doable to you? This is the same as 1 over x squared dx. 0 goes away. That's not natural log. Please don't do natural log there. This is pi integral 1 to infinity. Just look at that as being x to the -2. And then use your power rule for antiderivatives. So what would you get? You get pi, and then it would be times -1 over x. That's the antiderivative of x to -2. And you want to evaluate that 1 to infinity, right? Now, I didn't do a limit. We're supposed to do a limit here, aren't we? Because that infinite. But we can kind of think about what would happen here. If I replace this x with something that was headed to infinity, what would this turn into? 0, right? So when we plug in infinity, we should get something headed to 0 minus, now let's plug in 1. Plug in 1 here, we get I don't know why I put a negative in front of this. Sorry, everyone. You see that negative? No idea why I put that negative there, honestly. There was no negative there. It was just the pi and then the negative 1 over x. I think that's what I did, but that would mess up our answer. So here we plug in 1, we get negative pi here. And then when you subtract a negative, you get plus. So you get pi. Huh, interesting. That's a weird. That is weird, right? If you take the graph of 1 over x, wrap it around the x-axis, and fill it up, it will take a finite amount of volume to fill it. Pi is the volume of that thing. You could actually define pi this way if you wanted to. You say pi is equal to the volume of the solid generated when you take the graph of 1 over x from 1 to infinity and wrap it around the x-axis. That's what pi is. If you wanted to, you could define it that way. It's a weird way to define pi, but you could. Okay, so at the end of the day, the volume of this is finite. Finite, right? You have a finite volume. Let's do surface area. Okay, so for surface area, I'm going to use the same formula we just used. We have a function of x, right? So 2 pi integral from 1 to infinity. What goes first? F of
1
x,
over,
which for us
yeah.
is 1 over x, right? Times the square root of 1 plus. Now, what do we need here? The derivative of the function squared. Now, I haven't done that here. So let's do that on the side. If y is 1 over x, which is same as x to the negative 1, what is the derivative of that? Negative x to the negative 2, which is same as negative 1 over x squared. Take that and square it, and you should get 1 over x to the 4th. So I add to that 1 over x to the 4th dx. All right. I'm almost out of time. I need to finish this. Are y'all ready for the next thing? All right. Couple of things. Do you agree that if I am plugging in values between 1 and infinity, that this 1 over x is a positive number? This is always positive. Do you agree that everything under this root is always positive? Yes? Do you agree that what is in yellow is bigger than 0? Yes? No matter what x I plug in, as long as I'm plugging x's in, well, that actually doesn't matter because I'm going to take it to the 4th power. But y'all agree that that's bigger than 0, yeah? And so do y'all agree that 1 plus that number, whatever it is bigger than 1? Yes? And then do you agree that the square root of all that is also bigger than 1? So like if you take a number that's bigger than 1 and take its square root, it's still bigger than 1. Y'all agree with that? So everything here in blue is bigger than 1. So would you agree with this statement then? That what you see here, the whole integral, is bigger than or equal to 2 pi integral 1 to infinity of 1 over x dx. Because you just told me everything in blue is bigger than 1, right? So if I replace everything in blue with a 1, right? Take everything in blue and replace it with a 1, then this is smaller than this, isn't it? You have to see this. 1 over x is 1 over x, right? This blue part's bigger than 1, which means the whole integral should be equal to the same integral replacing the blue with 1. You all agree with that? What's the antiderivative of 1 over x? Natural log. So this is equal to 2 pi natural log x evaluated from 1 to infinity. But what happens here? If you let x go to infinity here, what's the natural log infinity of infinity do? What does a natural log function look like as you go out to infinity? It grows, it becomes infinite, doesn't it? And then when you plug in 1, natural log of 1 is 0. But the whole idea is that this thing is infinite. But our integral must be bigger than or equal to infinity, which means it must also be infinite. This is called basically showing that an integral diverges by comparing it to something that we know. We know this will do something. And so we know that this is bigger than it. So we know that this has to be bigger than this. But what is it saying? That the surface area is what? Which means I can pour exactly pi into it and fill it, right? But I don't have enough to cover it. It's called Gabriel's paradox. It is a paradox. We'll talk more about it next time. But it's weird, right? It's like you can fill it, but you can't paint it. There's a reason why. You should Google it. There's all sorts of crazy stuff on the internet about it, you know. Gabriel's paradox. It's called Gabriel's horn. If you've ever seen the angel Gabriel, there's an angel, I guess, in some religious, I don't know what it is, Christianity or what. There's an angel named Gabriel that has a horn. And so I don't know why they call this Gabriel's horn. The horn goes forever. So Gabriel can never really get to the end of it, but it's called Gabriel's horn. Like a horn, like a trumpet horn. All right, so do your homework for 7.2, or sorry, 7.2, 7.4, 7.5. 7.4 and 7.5. And then we will start chapter 8 on Wednesday, sequences and series. Here we go. All right, have a great day. Anything at home, questions?